This is set 2 of the review notes. I got to move the page here from set 1. Where's my page turner? There we go. All right, so moving on, we're going to do implicit differentiation next. A lot of people had this one wrong on the final. There was an implicit on there, so I might need to go a little bit slower on this. I can't quite read if that's an x squared. I'm going to assume it is. So remember, with implicit, we take the derivative with respect to x. That's really important, of both sides. This would be the derivative with respect to x. So remember, the derivative of x cubed with respect to x is just 3x squared. Technically times the derivative of x, but that's just 1. When we do the derivative of some function y, and again, think of y as a function of x, we still do 3y squared, but then we need to multiply by the derivative of y. So when we do implicit over here, we are going to have, boy, it's really hard for me to tell if that's an x. I'm going to assume it's an x squared and see how that works for us. Actually, I think I'm going to look at a paper copy first. Sorry, give me a minute. I just want to make sure it's actually an x cubed. Good thing I looked. All right, so this right here is an x cubed, not an x squared. So the derivative of x cubed with respect to x is just 3x squared minus, I do the product rule in parentheses so that I don't make a sign error. And if there's a constant out, like if it had been a 4, I'd put a 4 right here, and then I still do the product rule in parentheses. I do first d second, and then I do plus second, and the derivative of x with respect to x is 1. The derivative of y with respect to x is dy dx. It's y prime. So be careful with that. So we do first d second plus second d first, then plus 3y squared times the derivative of y. The derivative of any constant is just 1. I would distribute the negative in. I'd get a 3x squared minus xy prime minus y plus 3y squared y prime equals, sorry, that should be a 0. The derivative of 1 is, or any constant, is 0. Remember, we save all y prime terms over here on the left-hand side, and we move all non-y prime terms over to the right. So I'd have negative x y prime plus 3y squared y prime is equal to, move that guy over, minus 3x squared, move this guy over, and a plus y. The reason we isolate those terms with y prime over on the left is so that we can factor it out. And then once it's factored out, we can divide by it. So now when I go up, I'm going to see if I have this or some version of it. So on the top, I have a negative 3x squared plus y. That's this guy in reverse. I also have a negative x plus 3y squared. That's this guy in reverse. So the answer to that is C. Keep in mind, if I had been doing dy dx at the instant when at a certain point, like maybe -1, 2, what I would suggest you do is do the number plugging in before you start cleaning it up, because it's easier to work with numbers than with variables. All right, then we did related rates. There's such a huge process for related rates that I think instead of writing it all out, we'll just go through a problem with it. So we've got an airplane approaching an airport from the north at 181 kilometers per hour. A second airplane approaches from the east at 191 kilometers per hour. So let's put that airport here, coming in from the north, coming in from the east. These are rates of change. Let's make our triangle. So this guy over here, I like to call it dy dx, but you can call it anything you want. That guy's going at 181, but keep in mind that we're getting closer to the airport, so we'll use a negative because that distance is shrinking. A second airplane approaches from the east at 191, so I'll call that dx dt, and that will be a negative 191. Find the rate at which the distance between the planes changes. Let's maybe call that distance z, or even capital D for distance is nice. I don't like z's, they look like 2's. So I'm looking for dd dt at the instance when the distance between the plane, when the southbound plane is 35 kilometers, so that would be y equals 35, and the westbound plane is 21. So this is a Pythagorean one. We'll just start it, probably won't finish it. So we know that x squared plus y squared would have to equal d squared. And remember, constants can go in our pictures, but as these are changing, so is d. D will be shrinking as well. So I'll take the derivative with respect to x of both sides. I'll do, oh sorry, with respect to time. Time is my variable of change. Better go fix that on my picture. Getting a little sloppy here. So I would have the derivative with respect to time of the left-hand side, my derivative with time being my independent variable of the right-hand side. That gives me 2x times the derivative of the guts, which is dx dt, plus 2y times the derivative of the guts, which is dy dt, would be equal to 2d times dd dt. This is where we plug everything in that we know and find what we don't know. I would factor a 2 out of everything. I'd go back to my picture. I'm stopping these planes when x is at a 21. dx dt is a negative 181. Y would be a 35. Sorry, I keep scrolling, but I forgot those numbers. And dy dt is, actually I got these swapped. This is 191. For dx dt, dy dt is negative 181. Don't know it. Times don't know it. But this is what I'm being asked to find. What that means is when something's missing, it comes either from the stem of the problem or from the picture. And if you go back up here, I'm stopping this at the instant when. I didn't put them on my picture at the beginning because they were changing, but once I stop that clock, I've got x being 21 and y being 35, which would mean this would be the square root of 21 squared plus 35 squared, a la the Pythagorean theorem. So I'm not going to go to a calculator. We'll just go like this. This would be the square root of a squared plus b squared. And I would solve that for dd dt. All right, so our related rate process works out pretty nice. Then we've got our big existence theorems, I call them, existence. We use these when it says, is there a value C such that, or explain why there is no value such that. There's always some question about the existence of certain numbers. So the IVT hypothesis says that if a function is continuous, this one only requires continuity. Then, go put that on there. The EVT, the extreme value theorem, also only requires continuity. And usually these are on, I'm going to go like this, on some closed interval. Okay, so these two, the IVT, the intermediate value theorem, and the extreme value theorem, in the hypothesis, we only need continuity. The MVT and roles, by the way, it's these top ones that are existence theorems. The MVT and roles require that a function be, and roles really is the MVT, so you don't really need to memorize that one. If a function is not only continuous, but it also must be differentiable. Basically, graphically, we can't have any discontinuities or cusps. However, if they tell you that it's differentiable, a function can't be differentiable unless it's also continuous. So sometimes they'll tell you h of t represents the height of the water. H is a differentiable function. You get to assume continuity. Differentiability implies continuity. I think of Diet Coke. Continuity alone, though, does not imply differentiability. A great example of that would be the absolute value function. It is definitely continuous on its entire domain, but it's not differentiable right here. So Diet Coke, if they tell you a function's differentiable, you get to state, because h is differentiable and therefore continuous, you get to state that in your argument. All right. But if a function is stated to be continuous only, we can't apply this guy. So super important. We're going to spend more time on these three at a later date. But for now, I really want you to know the hypothesis of them, continuity and continuity, and then I'll discuss the conclusions and not write them out formally. What the IVT states graphically is that as long as I am continuous on some closed interval from a f of a to b f of b, I can have a cusp, but as long as I don't lift my pencil, I must hit every y value on the way. So it guarantees the existence of at least one place, one x value, such that f of c equals k, where k is between the two. So it guarantees at least one time where the temperature had to be 30 degrees if it went from 50 to negative 10. It's used a lot for verifying the existence of zeros. In a tabular form, what it'll often look like is this. It'll say, and again, you don't have to write all this down, but maybe there's some function and some, let's call it h of t. And maybe these are different times. At time 0, 2 seconds, 5 seconds. Let's do 7 seconds, 10 seconds, 12 seconds, and maybe we're charting, I don't know, let's call it temperature. If they tell you the function's continuous and they give you a table, a lot of times it'll say, how many times are you guaranteed, or it might even be like a yes or no question, or is there some time where the temperature had to be 0? If so, how many times, that type of thing. So really what you're looking for is sign changes. The function's positive, and at 2, I have no clue what's happening between here, but to go from positive to negative, I must hit 0 on the way. I must hit 0 on the way. I might have in here, but with this data, I can't conclude definitively that I did. Must have hit 0 in here. So there would have been at least 3 times where the temperature was 0. Could be more, but I'm guaranteed at least 3 times based on this table. And if I were, again, when you're using this argument, you have to say because the function is continuous, the IVT guarantees. All right, what does the EVT guarantee? At least one place, as long as the function is continuous, where a function must have an absolute max and it must have an absolute min. On any function that goes from a f of a to b f of b, somewhere along the way we had to have had an absolute max and an absolute min. And again, they can happen at cusps, so we don't have continuity, but at least one place. So if we don't have a max or a min, right? It means the function wasn't continuous. That was on the final, actually. All right, what does the MVT say? Well, graphically it says that on any closed interval from a to b, when I connect a f of a to b f of b, there's got to be at least one spot. It guarantees the existence of this sucker such that, oops, sorry. That's actually not the right spot. I want to draw it in the right spot, such that the slope of the tangent line runs parallel to the slope of the secant line. Basically, what it means is this average rate of change has to equal the instantaneous rate of change at least once. It guarantees this right here. Formulaically, it would say the average rate of change, slope of the secant line, has to equal the slope of the tangent line at least one place, as long as the function is both continuous and differentiable. All right. Then we had the fundamental theorem of calculus that said when we integrate some function from a to b, we find the antiderivative evaluated at the top of the interval and at the bottom, and then subtract it. Remember, capital F stands for the antiderivative. So if this was f double prime, what that means is I do f prime of b minus f prime of a. We're just taking antiderivatives. That was all over Chapter 4 test. The second fundamental theorem of calculus, and again, the names of these don't need to be memorized. It's just the processes and when to use them. It says that when you're taking the derivative of the integral from some constant up to some function, which I'm going to call u of x. Again, that could be x, could be 4x. I think on your test I had it be root x. The derivatives and the integral undo each other. They're inverse operations. So really what happens is I just get the function back evaluated at u. But then I also need to multiply by the derivative of the guts. And most of you did that right on your Chapter 4 test, so I'm not going to explain that anymore. All of this is a strength for you guys. So if you need to read this about, you've been really good and consistent with increasing, decreasing, your maxes, your mins, concavity. It's been really good. So I don't really feel the need to go over that, but if you feel the need to read it, you go ahead and do so. I think that was Chapter 3. Same with our concave up, concave down. We were really good at that. So I'm going to go all the way down here to linear approximations. All right. So a lot of times, actually not even a lot, on every practice AP exam I've ever seen, there's either been in FRQ, multiple choice, or both, some function that's given. Maybe this is, let's call it W for water level. And let's say that I'm just going to make my favorite fake function that goes like this. So this is the actual function. A lot of times what they'll do is they'll say use the tangent line approximation, also known as a linear approximation. Sometimes they call it local linearity. I haven't heard that on the AP test though. They'll say, all right, you're going to use this tangent line to approximate how much, let's say this is water, maybe in a tank. And as long as we stay close to the point of tangency, our error won't be very great. But as we veer away from the point of tangency, it's pretty high. So a lot of times what they'll do is they'll take this tangent line at, let's say, 2, and they'll say use the tangent line to approximate what's happening at 2.2. You'll be hardly moving away. The process is, first thing you need to do is take and write an equation for the tangent line. So I'm going to take this away so I make it more generic. I'm going to take this out too. I'm going to call this C, and that point of tangency C, f of C. Remember to get the equation for the tangent line, which we're used to calling y, which is fine, but in this case my y's are w's, so I'll alter that later. So let's even call this x f of x and make alterations. Sorry, making you erase. I'm doing this on the fly. So let's keep it very generic. Remember, it's y minus the y I was given is equal to the slope there, also known as the derivative, times x minus the x I was given. So I do want to call it c f of c. I apologize, because otherwise the x's with the x's is a little bit ambiguous. So back to here. Let's call this guy c comma f of c, and down here c. All right, so remember we're going to be looking for that y value, like how much water is there, right? We're trying to estimate. So I would do f of c plus. Now you don't need to memorize this model. I would just again do y minus the y I know is equal to the slope. Maybe they say at time, maybe that was 2. Let's make a fake one. At 2 hours in, the water level was at 29.4 feet. You'd go y minus 29.4 is equal to the slope there times x minus 2. The slope is always just the derivative, but what I'm saying is you can add this over. So when I'm done, actually, I would have a model, a linear model for W, because W is what Y really is. It would be f of c plus f prime of c times, and this would be time. Again, my model's accuracy is determined by concavity. You can see that concave down, I lie above the curve. So this value right here would be an overestimate. Whereas if I was on a concave down portion of the graph, say over here, my estimates would be under because my tangent line lives below the curve. So again, I'm going to give you a little bit better example of that. And then I think that's my last thing. Yep. So let's be a little bit better with this. Suppose in the stem of a problem it said that at time 0 there were 400 tons of trash in the waste plant or whatever. And then maybe there's a table that gives you T and the waste's rate that the waste is going up or down. Maybe it's that big plant out on 169 just north of Elk River. And we're charting the rate at which they're dropping off waste. And let's suppose right when the plant opens, the trucks are pouring in at a rate of, I don't know, I'm just going to make fake ones, 30 tons per hour. And then at time 2 we charted and it's 45. And then time 3 they're at lunch, so it's going down. And time 4 the end of the day is coming near. Time 5 there's just a few straggler trucks. And then at the end of the 8th hour of the work day we've only got 1 ton. Maybe this is in tons per hour and this is in hours. All right, just watch. You don't need to write this down. And at time 0, when the plant opened, there were 400 tons. So notice that I'm being given just a screenshot of the derivatives, a point on the curve. It might say estimate the amount of waste at t equals 0.5 using a tangent line approximation or a linear approximation, blah, 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 a tan line at t equals 0. All right, so I have no clue what my function w looks like. Again, I can see that it looks, according to my data, like it's kind of decreasing, but maybe it went up a little, down a little, maybe it went like that. I don't know. But what I'm going to do is go to time 0. I made a bad graph. Actually, I want to start it at time 1 just so it looks, and let's make this time 1. I'm going to go to time 1 and I'm going to do a tangent line, right? This would be at 1 hour in 30 tons. In order to do that, again, I would just start y minus the y I know is equal to the slope there times x minus the x I know. We'll make it more problem specific once we get what we need in there. What goes here? The slope of the tangent line. What's the slope of the tangent line? Well, it's 0.4. Sorry, I screwed it up. Let's call this 1/400 and then make that one. Sorry, I totally screwed it up. I'm such an idiot. No, just kidding. So I go y minus 400 is equal to the slope there times x minus 1. What's the slope there? 30 tons per hour. Now I'll make it more specific to my problem. The amount of waste, according to my tangent line, would be the 400 that I had at the beginning, plus the rate it's changing for the rest of the hours. And I'd put t minus 1. So let's suppose that was at 1.5. Again, I'm just kind of shaking it up. If I wanted to estimate how much waste there was using my tangent line approximation, right, I would just go put a 1.5 here. Over or underestimate would be determined by concavity, so there has to be information in the stem of the problem that says either W is concave up or W is concave down, or sometimes I'll tell you W prime is increasing, and then you infer that W double prime is positive, which means we're concave up, which means we're underestimate. So sometimes there's stuff you need to deduce from the stem of the problem. We are done. 25 minutes. Not too bad. Call it a day. All right.